Thank you so much. And thank you for the introduction, and thank you very much for having us here, or having me here today. I've really been enjoying, I've been here since yesterday, I've really been enjoying seeing your school. It's my first visit to EKA, and I think it's such a beautiful environment, very envious of your beautiful buildings and a sense of cool when you walk through the space. It's very, very, very nice. So it feels like family, and I hope very much we'll find tools to work together soon. So thank you also for the invitation. I think it's a really nice nesting of different questions. I want to show some of the projects that we've been working on for the last couple of years. And obviously Cameron has already shown some of this work. Just to say a little bit about CETA. CETA, I still have this feeling that CETA is all new. I don't know if you feel the same, Fabio, but it feels still so fresh and young when we started all these things, but it is 20 years old. And I think CETA has been many things over a long time, and really the people that passed through CETA have also informed our practice and left deep marks in how we are thinking about our practice and the questions that we ask. We look at the sort of questions of robotic fabrication, new material processes, advanced modeling, remote sensing. And we work very closely in interaction with our master's group, which is Computation and Architecture, led by Paul Nicholas and Natalia Guillem, where we are looking at the similar questions, asking what can architecture become, how is it that we are working with materials, what is the future that we are educating for, and also what is the future role of architects, to not take for granted that architects somehow perform the same as 100 years ago, 50 years ago, even 20 years ago. I think that the tool sets that we're working with, the questions that we are addressing, the ways that we can design and fabricate are radically changing. And it's important that our educational environments and our research environments are very closely knitted to create those synergies. Maybe most fundamentally, and also what I wanted to talk about today is really the role of technology and the idea of technological development. So we work very much with an idea of design integration, where we ask how we can think of design as a driver for technological development, but also a sort of fundamental understanding that technology is not something developed elsewhere and ported by invisible hands to the field of architecture, but that we are continually participating in its co-production. And by that I mean not just the architects, but the questions, the sites, the programs, the work of architects is changing and challenging what technology can be. And I think that's a very different starting point from many of the technological traditions that sort of boundary our field. So we understand digitization as a basic research question, which creates new possibilities for what architecture must be able to do, how it's executed, and through what and by whom it is constructed. A bit close to your man and machine, no? So how do we ask also who are the people who are involved? And in our part of the field, and here I talk very broadly about all of us in the digital design field, I think the idea of sustainable practice has been quite fundamental for the whole foundation of the field, but it has very much been linked to a question of optimization. So it has been under the remit of smarter with less. How could we optimize our practices and de facto build lighter so that we can reduce our impact on the environment, on resources, on transport, and on pollution. And in our work, this has also informed a breadth of projects, which really span across these 20 years of architectural investigations that we've been involved with, and where we have been asking really how computation allows us to ask with new ways to work with traditional materials or traditional ways to work with new materials, how that really allows us to think very differently about what materials can be, and exactly where the role of representation, the computational model, the information model, changes its role inside of the practice. And where we can connect with new ways of shaping functionally non-standardized materials, optimized at a micro level, with the sort of breadth of architectural practice. So I think there's an underlying theorem. I think it has different names in different parts of the field. In a way, it feels like every design group or computational design group has its own name for this. But I think what's underpinning it is really a rationale or a theorem. No, nobody knows if it's true or not, but a theorem, which is that by formalizing material properties and behaviors and devising means of representing their inherent complexity, we can access the underlying compositional logics and thereby gain agency to their steering. I think in many ways what Fabio was also showing today was also this sense that you can somehow steer the material logic, the structural logic, and thereby also gain, when we are showing these foam experiments, now how do you steer these material systems? I think we should remember that this is a theoretical position. And I think when we start designing, new boundaries for our field, also becomes, well, what is the material system that we're trying to develop or that we're trying to interact with, and that we're expanding our system boundaries as we start working with living materials and engineered materials, so that what we are steering is not only a piece of steel or some concrete or so on, but also organisms that have symbiotic relationships and are co-producing our designed spaces. Yeah, so this idea that we can understand, represent, and control in order to functionalize material systems for architectural use. I wanted to sort of take that as a springboard to think about or think through our newer projects to start setting some questions to that theorem. And here I wanted to talk about the EMA project, the eco-metabolistic architecture project that we've been working on for the last 3 years, and we have 2 years left, which really asks what are the transformative shifts that working with biomaterials have. And here, of course, in the field, we see a lot of movement towards bio-based materials, towards timber, towards renewables, and there are very straightforward sustainability questions that lead us into this. But I think also what's very interesting about it is it's a relatively uncharted field. So, of course, timber construction is 20,000 years old. We've been built with timber forever. But at the same time, only 10, 15 years ago, timber was still considered an experimental material, a material that is difficult to control, difficult to fire regulate, and difficult to actually engineer in more than single-story or double-story buildings. So what we're asking in the EMA project is really, how do bio-based materials in a broader range allow us to think very differently about architectural axioms such as durability and permanence. So it changes our understanding of value, of durability and fabrication to work with materials that are essentially metabolistic, that have embedded into them a sense that they will, a system of return, or a system of biodegradation. So designing with bio-based materials present 3 core challenges to architectural thinking. First, it asks us to instrumentalize, to make worthy or valuable different strength ratios and durabilities. Now, the bio-based materials are essentially weaker and less durable than their finite material counterparts. Secondly, it argues that materials are part of systems of return, and that the additional life cycles must be considered as part of a design system. And also, it presents a new sense of agency as we participate in cycles of growing and harvesting materials. And here I mean in the really big sense, yes, grow, harvest tree, but also grow, harvest algae and bacteria, and the breadth of material systems. And this leads us to a very different ideal. So as Cameron also was showing before, I think what we're interested in this picture is this idea that some of that thatch is new, done last week, and some of it might be 300 years old. So how do we build buildings that are continually constructed, that are continually addressed, and how do we develop systems that are able to think about materiality across multiple life stages and orchestrate their systems of replacement or systems of repair. So sometimes I feel like it's interesting to remember, Corbusier looking over the Pantheon, or, what was the modernist ideal? It was an idea of durability through material solidity. And when we turn to bio-based materials, we start seeing something that has a very, very different temporal clock. And in reality, it is not so novel. We have been repairing our buildings forever, but we might move our gaze and look towards that kind of time, where time is constructed through ideas of re-engagement, and therefore build ideas around stability and endurance as performed acts, something we participate in. Big piece of rock lasts forever, or I participate. I'm very curious towards that. Again, I also want to just put a caveat into this. I think it's really important when we work with bio-based materials that we remember we cannot grow ourselves out of the problem. It is not possible to place ourselves in a fully renewables economy. There is a finite amount of photosynthesis happening on the planet, and the moment we start using that photosynthesis to grow plants for built environment products, food, all of that, there's something else that suffers. So I think it's more just a curiosity. How can we build new models, and how can we bring these models back to a more holistic way of thinking about circular design and replace circularity. Yeah, so I'll try to come back to the script here. So in ways that we have been looking at this is also a critique of the circular design framework. Again here, as Cameron also did, placing the Ellen MacArthur butterfly diagram as a sort of core inquiry, because here we see cascading, and we also see the difference between the blue side, which is the finite materials, steel, concrete, and then we have the green side. And we can also see that here things are not really cascaded, but they are rather sort of metabolistically downgraded, finally ending up in energy. What we're curious about is how can we build new models on this green side and kind of fold the butterfly together to find new ways of working with finites also. Challenging us to think very differently about lifespan. These are drawings of small huts in Christiania done by my students in the US, who are really looking at how do we think tectonically about how materials are placed together, but also temporally thinking in lifespans, placing the deeper lifespans at the bottom and the shallower lifespans at the top. and placing ideas of continual construction around ideas of technological development. And one of the key things we've been very interested in trying to develop is ideas of placing fabrication into these cycles, thereby challenging the sites of production and also the idea of technological development. This is Roxandra, PhD at CETA, where she's looking at additive manufacturing for repair, working with these bio-based polymer composites that Cameron showed before, and then developing her own repair strategies that are able to conformally print on top of prints to create this sort of layered world. This is also what we've been discussing in a symposium that we had here in 2000. It's in May this year in Copenhagen, and also the subject of a special issue that we're developing with an artist journal from Milano, looking at broken world building. And here I think it's such an interesting concept, the idea of broken world thinking coming out of science and technology studies from the Anglo-Saxon context. I think it's quite American and UK-based theoretical field, in which it comes out of sort of ideas for media studies and telephones and repair workshops and that kind of world, where Stephen Jackson from Cornell very assertively positions that the world is always broken. Rather than thinking of breaking as a failure, than to think of breaking as a condition that is permanent, and that our way of dealing with this is strategic. We build up tactics, and that these tactics can allow us a very different kind of understanding of what it means to develop technologies. So an interesting example in his work is the building of the internet, and he analyzes the building of the internet and shows us how the building of the internet is the hacking of endless amounts of disrepair, and that constructing this big innovative piece of technology is not thinking everything from the start, but rather constantly strategically dealing with failure. So in that way, he talks about repair as being both normative. It is both the actual repair of that piece of technology, and it is also ontological. So it means that it's also about a whole other understanding of how we make meaning and where we positioned in respect to our social worlds. So it asserts that breakdown, dissolution, and change, rather than innovation, development, and design, are, as conventionally practiced, are the key problems that are facing new media and technology scholarship today, and that suggests very different starting points for architecture, rooted in a radical rethinking of lifespan, material engagement, and reconsideration of systems of return. So in CETA, we're very inspired by this because it sort of changes our foundations, both in the condition of architecture as well as its invention. So how is it that these technologies are orchestrated? Where are they placed? How do they move from the comfortable, secured walls of the lab and start breaking through and positioning themselves in response to environment, ecology, and sociality? So I wanted to show a little bit of examples, and we are tentatively, it's a working model, trying to distinguish ideas of adaptation, repair, and care as different moduses of these reparatory theorem. And so we sort of think maybe adaptation to timber, so how to work with harvested materials and material reclamation. In this project, we are looking at, Cameron also mentioned this, we're looking at building, reclaiming our own materials. So as Cameron was saying, then we built these installations a couple of years ago, and we're now looking at how we can reclaim these elements and reposition them into new in new lifespans, new architectures. Here we're building a little shelter. It's a small shelter to sleep in. We're putting it into a forest. And we're then, what we were doing in this project that we're reclaiming the material from, is we were working on making these design to fabrication workflows that allow us to very intensely understand material performance, material qualities, and be able to orchestrate them. So as you can see here, we are making these glue lamps, and what we were doing is we're collaborating with Microtech, it's an Italian company creating these CT systems for timber logs, where we get a very small data set in which we can see the variation of material quality, and then to make direct interfaces between these material maps with the actual structural performance. So we're in a way structurally optimizing from a material level, allowing us to orchestrate. We, of course, in a beam, the material that's in the middle is less needs to have less quality than the material at the edges. We know that we have to have high quality around any kinds of joining, and we can therefore create these material variations, which is very ordinary in glue lamp construction. We often vary the different materials, but we're doing it sort of at a hyperscale and design integrating it. So we have a lot of knowledge about these beams that we want to reclaim. We know where the knots are, we know where the material intensity is changing, and we want then to find out, well, how can we put them into new structural systems and redeploy these material maps that we have of them. And this is turning out to be much more complicated than we thought. The beams are double curved and so on. They have moved. Also, there's data missing. There were hacks done in the fabrication environment that meant that even though we have a fabrication data, things changed. This is totally normal. And so therefore, to retrieve this information through ideas of the history stack is turning out to be very complicated. At the same time, it's a composition. So we're not only working with one material stream, as in any kind of building, we have multiple material streams. Here we're working with Luleå Technical University, and Omtre. Wendy was here this morning. I think she had to leave. And Omtre is a Norwegian company that is looking at reclaiming timber, and they very kindly gave us some old barn timber and also some very mysterious 2x1 sort of struts. And what we're then looking at is, okay, can we put them into the same material or the same digital workflows? Can we CT scan them? Can we build material maps of them? And can we integrate them into these sort of strategic optimization workflows? I think what's really interesting about that is about understanding, sorry about quality, understanding how materials, where do these material streams come from? What do we actually need to know about these materials? When we work with reclaimed timber, they are much more heterogeneous than when we work with virgin timber, and we need to develop methods by which we can recertify these materials batch by batch, which means that we need non-destructive methods of certification. And also, we drew this diagram, Martin and I, literally yesterday, I think. So also a bit curious to it. Very much in flow. But what we can see here is that the streams of materials are constantly coming in. We are constantly needing to represent them and to match them into these complex assemblies and then bring them into next lifespans. So how is that orchestration actually happening, and what kind of knowledge do we actually need to build about these material reclamation streams? A second sort of overarching question is the question of repair. And here we're using the biopolymer composites as a material system to really think these things through. The interesting thing for us about the biopolymers is really the recipe aperture. No? So they are built, they are designed through these different recipes, and it's a space. It's not one optimized material, but it's a set of different materials where we can vary the recipe in response to, first we thought structural performance, now make it stronger, make it weaker, make it, you know. But we learned very quickly that when you're working with the circular design, then it is the idea of these sort of waste streams, as we call them, it doesn't exist. Markets can be very quickly saturated, and material flows that you might have depended on in 1 year can change very dramatically 2, 3, 4 years later, either because of new industries absorbing material resource, or simply because there was a bad harvest, or it can be very different events. So we enter a place where material flow becomes very dynamic, and we need resilience in our way of understanding material systems to be able to navigate those. So in the biopolymer track, we call it, we're looking at these different material systems, and we've been doing this different material flows and looking at how we can compose architectural paneling systems from different recipes of biopolymers. I think we saw that before. And obviously also working across disciplines to be able to characterize these material recipes and their changes. So how different are they actually, and what is the difference that they're purporting when we start changing the materials? Here Gabriella Rossi has been doing her PhD looking at how we can use machine learning to navigate the recipe space. So if we sort of imagine, let me just that I'm putting in these different material sources, different cellulose sources coming from different bio-based and waste-sourced streams, and then, and then I want to understand what is the difference between these materials and how do they perform differently, both in fabrication and in structural performance. Right now, we're working on a project called, we gave it a name yesterday, Riserial, I think. Anyway, it's a vault system where we're trying to 3D print with these materials and grading these materials. So we build an extruder head that can have multiple recipes at the same time, and where we are able to create these sort of vaulted panels and put them into an architectural system where we can really understand the flow of the material and also the recipe variation, compositionally as well as performatively. Which leads to questions of durability. So in these projects, maybe we're more interested in, they're placed inside there. We have very big humidity differences in Denmark, as I'm sure you have here in Estonia too, but they are very well protected. Once we start placing these materials outside, we get very different behaviors. And what we're interested with that is really to try to understand these systems, not necessarily as a mature building system with which we will make architecture tomorrow, but maybe as a sort of model system by which we can start understanding the methodologies that we need to put into place to work with temporal material systems, temporally changing material systems. And our students are right now in Norway. I got sent images from the stave churches that they visited yesterday, and I think it was really beautiful. So I don't know, how old are they? 600 years old, 400 years old, something like that. Very, very old timber structures. And what we can see there is that the shingle is exactly temporally stratified. So there's shingle that is 300 years old, there's shingle that is 100 years old, and there's shingle that is 20 years old. So that where this becomes maybe a bit mystic, what are we actually studying here? Are you going to build a building that's made out of bone glue? Then this idea of a temporality in the building is, I think, something very direct. So what we're trying to do is find ways of analyzing this and being able to characterize material systems over time, and also to build a new vocabulary by which we can start thinking about these material systems. So new topics such as diagnosis, repair strategy, building pathology creeps in from other fields such as conservation and preservation. I think these interdisciplinary surfaces are incredibly inspiring. In our work, we are really interested in this idea of design for repair. How do we design systems that are open for repair and where repair is somehow pre-thought, while at the same time understanding that reparatory action will always be strategic and changing. So here we can see the virgin material, the weathered material, and then the design paths and the methods of conformal printing. I'll just skip that. Yeah. These are also questions we're looking at in the studio and at UPenn, where I'm deploying their amazing representational skills at UPenn to start speculating how would this sort of temporally layered architecture actually be composed? What is its sort of choreography? And how do we start understanding a new language for architecture, which is maybe has deep roots in ideas of weathering and so on, but maybe start giving us other kinds of hooks on thinking about material change. So the last project I wanted to show, and this sort of architecture of the timber with 20,000 years of tradition, biopolymers with maybe 100 years of tradition, and then here what we're working with is really the idea of biotech, which maybe has a 30-year tradition. These different technological platforms to sort of involve them as part of the foundational architecture of the bid. So it's sort of deliberately very, very broad project. Here we're looking at really how we can work with living systems. And in the case of Pepe Yoka, collaboration with the Soft Matters Lab in Paris, we're looking at how to, I hesitate to say, but it was to functionalize these living organisms that are light emitting. This is a terrible light source, just to say. I mean, I'm a little bit night blind, to really, on a bad day, you have to stand in there for a long time. So it's not about making a new lamp or something, but it's about trying, what are the methodologies for thinking, how do we even understand what it means to be building with living materials that are kept living, no? And what are the sort of care protocols? What does it mean to invent care as an architectural subject, and what are the protocols of care that we would need to develop to work with this? So in this project, we're actually just designing a bioreactor. Many design projects have looked at bioreactors before, and what we're trying to do is really try to understand how are they built in time? So what are their performances? What are their lifespans? And what is our engagement here? Inoculating, feeding, evacuating waste fluids, and so on. What are these new circularities that we need to develop to be able to do that? And how do we construct new representations that are able to denote the propagation of bacteria through matter? So obviously a very different understanding of metabolistic architectural tradition. Yeah. Anyway, if I'm allowed I have 6 minutes. I'm just going to give this 3 words. I love this project. It's this big, but what we're doing here is we're using the capillary action in natural fibers to be able to build an embroidered surface. So it's embroidery, machine embroidery. And then we are the capillary action of the fibers are sucking up the inoculated fluids and creating this really beautiful living tapestry. A very small tapestry, but still, I think it just has such poetic understanding of new ways of thinking about narrative and story making and architecture here in collaboration with a living species. I think maybe we could also ask with Fabio if whether this is beautiful or not. No, what I think when you say beautiful, I think you mean, is it meaningful? What kind of meaning is this constructing? I think I think it's a really interesting, very open question. Anyway, so if we return to conclusion, then I wanted to sort of end with some perspectives in a very sort of concrete sense. We are right now starting 2 new projects. Martin Tamke is starting EIC project called ROAR, where we are exactly looking at material flows of bio-based and waste-sourced materials, where we're collaborating with ITKE, Luleå, as well as a whole host of other partners, where we're exactly trying to figure out, well, how do we characterize materials? What are the modeling frameworks to be able to do this? And how do we make batch by batch material characterization? So non-invasive or non-destructive characterization. In our work on timber, so inside of the EMA project, acting as a pre-project for this, what we've been doing is looking at these CT scans, but also other kinds of models such as acoustic, we're hammering the timber to be able to understand the performance of the timber. So what models are there for that, and can we benchmark them against each other? How do we make these technologies tractable, portable, localizable? Obviously, what we're doing right now is moving timber across Scandinavia to go to the CT scanner that's all the way up in Skellefteå. Oh, no, it's like super far away. So we have crazy LCAs because we're moving all this timber around, and it is perhaps not the right model. But then what are the sort of low-tech, high sort of self-tech methods that can replace these? A second project, which is also a pitch because it's a network, it's an open network, is led by my colleague Paul Nicholas, where he's looking at blue biomass. It's a collaboration between Denmark, Australia, and the UK, and looking at really can we source materials from the sort of blue biome, understanding biomes as not only belonging to agriculture or the forest, but also to other kinds of sources, and asking us really about what is the regionality of our materials and the impacts that their extraction have on our direct ecologies that we take part in. And with this, I think there are a series of very large questions that belong, and maybe many of our lectures in these years kind of start here. But I think all of this is then somehow to find the methodological underpinning. I mean, how are we going to think about this? With what technologies are we going to afford this? And how do we even think about how technologies are developed and co-created in response to ecological and social settings? I think when we look at this, we can see that there are very, very large indicators that are pushing us towards these things. I think that we are in a schizophrenic moment now in CETA, because then a lot of this is very basic technological development. We create new monitoring frameworks, we're creating new machine learning algorithms, we are developing new printing technologies. But at the same time, I think it's this sort of it's a balance. No, or a balance sounds like it's in negotiation of each other, but maybe it's just two-faced. No, at one hand, yes, we're interested in the direct technologies that we're developing. Cameron was showing very clear understanding of what these workflows needs to do, how we can actually encode them, etc. And at the same time, we're also curious to the deeper ontological questions that they bring forth. So I love that when I walk through CETA, I will see projects that I don't really even understand. I'm wondering what the hell is that doing here. I think that sort of richness of sort of expansive exploration and testing, I think is a really fundamental part to not only our practice, but to our practice as a whole. So, thank you.
Thank you so much, Mette.